All right, so there may be a bit of an echo in here. I realize now I'm recording from a different location, not at home, and it's taken me a while to think about how I want to present this material. And the reason is, well, Chapter 3 is the most conceptually demanding part of the course. The second half of Chapter 4 is computationally the most intensive. And it's just the reality that if you want to solve a driven damped harmonic oscillator by hand, it's a page or two of pencil and paper. Now, ordinarily, this is fine. We spend time in lectures, we work it out, I have you do some examples. It's fine. The reason I'm hesitant is that I suspect that many of you, like myself, are rather fatigued, and I'm hesitant to dump a bunch of calculations on you. So I'm still trying to figure out how to deliver some material so that in your subsequent courses, when somebody talks about this, you can say, oh yeah, I remember doing something like that. While at the same time, not having you start a problem and throw your hands up in the air and go for a walk. So with that in mind, the second part of the top hat, where this video is located, I've just kind of broken up some of the things we're going to look at. In Chapter 4, we have the techniques and principle to solve a wide range of higher order linear differential equations. And we're not going to. Instead, we're going to focus just on harmonic motion that's driven. So I want to look at these cases with you and talk about how I'm going to pull together the rest of the course. So this equation here, which is x double prime plus gamma x prime plus omega squared x equals f of t. It's non-homogeneous. F of t is the driving force. Gotta make that more mathy. And this is the only differential equation we're going to think about. Now that's still quite a few, of course, but hopefully by focusing on just one differential equation that represents overdamped, critically damped, underdamped, undamped, and all the things that can happen with that. So if you're a circuits person, think LRC circuit. If you're mechanical, think some sort of damped suspension system or whatnot. And we're just going to focus on this one case. And we're going to try out new techniques on this one case. Now, case 1, we have x double prime plus omega squared x equals sine omega 1 t. Now, why the difference? Well, case 1 is we're going to drive the system at a frequency that's different than the frequency of the system. So there's some force acting on this system, or some voltage source, if you're thinking of circuits, that's operating on a different frequency than the natural frequency of that system. Now, I didn't solve any of these things by hand. I just used Wolfram Alpha. And I think for the most part, I think you're going to do the same on certainly the next quiz and on the final and stuff. I'm going to have you make use of technology. I'm going to ask you to think about what things mean, of course, and I'll probably give you a couple questions, pretty straightforward questions that I ask you to do a step-by-step, just to check that box. Now I figured out I can embed graphs from Desmos into Top Hat. I don't know if they're clickable. I don't know what happens if you can open this up and look at it or not. But what we have here is the blue line is the driving force, and then the red line is the response. The red line is the solution. All right. So what do we have? We have a simple harmonic oscillator. It's being driven by some sort of force. And so the motion is a little bit different, you can tell, right? The amplitude is not the same. And that's because there's this force that just happens. I used something with half the frequency, right? So the natural frequency of the system is 2. the driving force has a frequency of 1, and so it just happens to be in such a way that it sometimes drives this down deeper and sometimes drives it up, right? Case 2, this is maybe a more interesting case. What if we drive the system at the same frequency? So here, x double prime plus 4x equals sine of 2t. All the initial conditions are the same, by the way. What we get, and this comes about through that stuff in 4.3, is we get an extra trig function with a t. And I talked about this in the above video lately, the first video, this top hat. And you can imagine what happens here. Sine and cosine oscillate between plus or minus, whatever. They don't grow or shrink. But this function is going to grow. And this is what happens to it. There's some initial funny business in the beginning, but the driving force, which is the sine function, it's not very large, right? It's sort of 1 unit per time, is big enough because it's at the same frequency to drive this purple response larger and larger and larger, right? So on the purple curve, right, this part here would be when the spring is all the way compressed. The moment this happens, the driving force is now 0, and the driving force is positive through the entire motion of the mass from compression to maximum extension. And as it hits maximum extension at just that moment, the driving force is 0, and then the driving force is negative, back towards compression. So if you think about, again, a kid on a swing set, the idea is, what's that thing, you call it an underdog, right? Where, the kid is swinging towards you, and as the kid reaches maximum height, you run up, grab the swing, and you push the person on the swing all the way back, and then you keep on running. Well, imagine if you had a pair of people doing that in both directions. So the moment you finish running under the swing set and you let go, somebody comes up, grabs the swing, and runs back the other direction. And as soon as they let go, another person comes up, right? You would very quickly have this huge amplitude of oscillation. And this is resonance. And this can be destructive if left unchecked. Although this is an idealized situation, this can't grow without bound. But if a system is very lightly damped, you could grow it quite large through driving. Another interesting scenario. These are both undamped, by the way. So, up here, this was undamped. This is undamped. And then this is also undamped. This is when the frequency is very close. So, suppose same differential equation almost. The frequency is 2, and then the driving frequency is 1.9. This gives us a really messy equation, but we don't care because we had Wolfram do it for us. We had this really interesting graph. And notice the horizontal axis. I've really zoomed out here. It goes from 0 to 400. If you only look at like 0 to 10 or something, it looks like you're seeing resonance again. And what happens is it doesn't quite get up there because it's not perfect timing. Certainly, it is driving the amplitude larger, but it's just a little bit out of time. And so at some point, it kind of gets in its own way, and it drives everything back down quite small. The vertical axis is not big on this. This is 5, this is 10. And so the oscillation goes down to almost nothing, and then up to 5 again, right? So kind of like a... So there's a frequency here that's happening inside of another frequency, right? The red curve has a frequency, and then there is sort of an envelope around this red curve that has another frequency. Yeah. So, and all of these are topics that you could spend a lot more time on, we're kind of going over them a little lightly here. And then, let's see here, just do a little case here. What about a constant driving force? This does more or less what you think it might. It shifts the oscillations. So it's not just a vertical translation, but it is similar to a vertical translation because the spring is being stretched and compressed a little, stretched and compressed a little. The spring is stretched all over here, and so things they're not even. Now, for the case of driven damped oscillations, so we're just looking at an underdamped equation here, x double prime plus 2x prime plus 2x. So this is underdamped because you'd have 4 minus 4 times 2, which is 8. That's negative. Just picked 2 here. It'll end up being the damped frequency. Now you don't have the same sort of thing here. Even if you were to zoom out, you won't. In fact, I can show you. If we go to Desmos, and where is it? Let's see. It's not exactly this one, but this one's close enough. And so you have initially some decay, which is what you'd expect, because the homogeneous solution has a negative exponential. So the homogeneous solution is decaying fairly quickly. But then you have this driving force, which doesn't really care that it's decaying. So whenever the driving force is positive, it's pushing the mass to extend the spring, and wherever it's negative, it's compressing the spring. It's pushing the mass to compress the spring. And so this purple curve is the driving force, and it drives motion that, let's see if we can zoom out a little bit here. This becomes quite regular. The homogeneous, if we just get rid of the driving force, the homogeneous solution decays away, and all we're left with is the particular solution. The particular solution is the long-term behavior of a underdamped driven oscillator, because the homogeneous solution decays exponentially. So that's kind of interesting. You don't get resonance in the damped case. I paused for a second. So you can't get resonance out of damped harmonic oscillation, because the principle of resonance is that you're pumping energy in and no energy leaves the system. It grows to infinity. However, if your input force is much larger than your damping, you can get some resonance-like stuff. And Wolfram hasn't been too happy with me. I've been experimenting, and I might continue to experiment. It tells me things like I've run out of computation time. So one thing you can see, though, is right here I have a differential equation. It's got a gamma of 0.5, and then it has omega squared of 4 and sine of 2t. So this is pretty weakly damped. It's like a system that has a natural frequency of 2 that's weakly damped. And it's not going to give me a solution because it wants my money. But you can kind of see from this graph that there's that same stuff we saw before, but then it grows quite a bit. Now it's gonna stabilize here, but it is going to grow a bunch. I'm kind of curious to see if it'll keep giving me graphs if I keep messing with it. So now the gamma is quite small, right? It's just 0.1. So now look, this looks a lot like resonance. It's still not going to happen, though. And the reason it's not going to happen is that sine of 2t is not in the kernel of this operator. And even if you'd made something that was in the kernel, you put an exponential here, you're just going to end up with t times an exponential, and that's going to decay. So you can't mathematically, you can't physically get resonance in a damp system, but you can certainly drive a damp system. We'll see if I'm able to convince Wolfram to let me do something more with this. Now, if you're a glutton for punishment, you can certainly prove this mathematically doing some calculations, but nobody's got time for that. We're all just surviving here. So there's an overview of some interesting things that happen. I'm not going to ask you any questions about these because I don't feel like writing them. The quiz on Friday will be fairly light. This is a good time to recoup, and the Laplace transform is going to require some work, so that'll be next week. All right, take care.